evolution of galaxies. And in this subject, the study of fine structures, such as tidal tails, stellar streams, and shell, is very important, because these are collisional debris that are created during the collision and mergers between galaxies, and they imply different collisional scenarios. For instance, here you have on the top panel example of tidal tails, which originate from major merger between two massive galaxies, and they are visible for about 2 gigayears, according to numerical simulations. Then on this panel, you have example of streams, these elongated structures here, for example, and they come from minor merger. So with a merger between a massive galaxy and a much more minor galaxy. And here you have example of shells, which are concentric structures visible here, which originate from intermediate mass mergers. And so it is very important to identify the fine structures in images in order to be able to reconstruct the past assembly history of a galaxy. But these structures have a low surface brightness, and so they are very difficult to detect, and we need deep images. So to perform galactic archaeology outside the local group, we can rely on the study of the diffuse light, which is emitted by these collisional debris. And we can do it, for instance, with the MegaCam at the CFHT. So here I'm going to talk about MATLAS, CFIS, and NGVS, because these are the survey we worked with. And here we have the spatial coverage of these 3 surveys. So MATLAS, the little blue patches here, perform pointed observation of nearby massive galaxies in 2 to 4 bands. Then NGVS, as we previously heard, covered the Virgo cluster. So here is the yellow footprint. And CFIS, we will have a presentation on it later. CFIS covers a large area on the northern hemisphere. And here is the footprint of last year, so less than 4,000 square degrees. And these 3 surveys are very interesting because they are LSB, low surface brightness optimized surveys. And to show you an example of what it means, here are some examples of tidal structures. So on the top panels are tidal tails, middle are streams, and at the bottom are shells. And you can see superimposed with the deep images, in the center, there are shallow images, like in here or in here. So on the right is pan-stars images. The center is pan-stars images. And the left images are MATLAS, and the right are CFIS. And clearly you see what is the interest of this type of surveys, because you discover a whole bunch of tidal structures that were not visible before, because the surveys did not have the proper depth to see them. And although CFIS here on the right is slightly less deep than MATLAS, for example, we are still able to see beautiful tidal tails like in here or there, or streams like visible in here, and shells in many galaxies. So once we have these deep images, the next step is how to characterize them. Well, there are several types of studies when you want to characterize the morphologies of the galaxy based on visual inspection. Either you have large sample of galaxies with many contributors, and then you can do something like the Galaxy Zoo project. So ask citizen scientists to perform a simple census of morphological features. Or you have a limited sample of galaxies with 1 contributor, and then you can perform a detailed analysis. But our approach lies a bit in the middle of these 2, because our goal is to obtain a detailed analysis of low surface brightness features, so not only simple morphological features, but low surface brightness features, on a large sample of galaxies, but with few contributors. And to do so, we developed an online annotation tool whose goal is to easily annotate and classify low surface brightness structures in deep images. So here you have an example of what the annotation server looks like. And it is based on Aladdin Light, which was developed here at the Centre de Données Astronomiques de Strasbourg, the CDS. And the goal is really to draw with precision the shapes of tidal structures superimposed on deep images. And so now I can perform a live example, a demonstration of how we can use the annotation server. So here's the interface where you can select the galaxy that you want with the survey, the type, and the band. And you just have to click on this thing here. And if I can switch, okay, if I can switch this, okay. And you arrive on this kind of image, which is the deep image. And you can easily navigate through the image, zoom in and out. And you can also display shallower image, like pan-stars, just I was mentioning before, to see the center of the galaxy. So let me get back to the deep image. So here's Cepheus. And now my goal is to draw everything that I can see. So here you can see that I'm using drawing buttons. So I'm selecting an ellipse because I want to draw the halo of the galaxy. So I put my ellipse and I superimpose as precisely as I can the ellipse on the image, and I attach a label to it. So here it's the halo that I'm annotating. Then I'm going to do the same thing for the stream that we can see. So I can select a snake or a polygonal shape. So this is a little bit big, but you get the idea. I can play with the size to make it match perfectly. And I attach the label stream to it. You can also see on this image that there are this feature, this filamentary feature, which is actually cirrus that are dust clouds from our own galaxy. And the problem is that, well, it's contamination because it prevents me from correctly annotating the structure. So the goal is also to annotate all the polluting sources that you can see. So here I draw a polygon to get all my cirrus. So you're supposed to do it precisely, but here I'm doing quickly. And you can see that there is a list of the pollutants that you can annotate. So the instrument, the satellite trails, the ghosted bright halos that come from internal reflection on the CCD, and so on. And so once you're done, you have here the summary table with your annotations and what it corresponds to. And when you press submit, everything is saved into a database from which you can do a lot of things. So let me get back to the presentation. Okay, so this is what I said. And from the annotation, the database, we can make measurements and perform analysis. The first point to take into account is the fact that we have several users. So we need to find a way to take their contribution into account. And then once we've done this, we can finally get quantitative measurements about tidal structures, such as the area they cover, their width, or the surface brightness. Also, we can develop several tools like thumbnails, which are very easy representation of the annotation. Whoops, not this one, which are very easy representation of the annotations. Here, the halo is in yellow, tidal features are in blue, because sometimes the image can get very crowded with many pollutants and many stellar structures. Thumbnails are a quick view to see how your structures look like. And also with our annotation, we can retrieve their masks. So it's very easy to perform automated aperture photometry, because once you have your annotation, you have the mask, and then you just have to sum the flux, which is inside it, to get an estimation of the surface brightness. So the next step is to remove the foreground sources that are present in our images, but we're working on it. And finally, an important point is that the annotation that we made are used for deep learning algorithm to automatically detect tidal features in deep images, but I will get back to it later. So we can get some results, and here I will briefly mention one. So we wondered, is our criterion to separate tidal tails from streams reliable? So we plotted the histogram of the width of tidal structures and of the surface brightness for tidal tails in blue and streams in red. And we found out that streams are narrower than tail, which is expected from models. And they also have a lower surface brightness, which might be age-related. Another result, which is important, is that when you look at the surface brightness of tails and streams, you see that you do not detect any feature after 27.5 magnitude per square arcsecond. And yet the depth of the survey of MATLAS is 29. So there is a difference between the limiting surface brightness of the survey and the median surface brightness of the features. And this difference must be taken into account in the future surveys when you want to assess their ability to identify tidal structures. And finally, I would like to talk about deep learning, because with Felix Richards, we developed a deep learning algorithm, which is based on our annotation dataset. And the goal is to automatically detect tidal features in deep images. And so he developed a network which is adapted to our segmentation problem with a small dataset. So we're talking about a few hundreds of annotation and sometimes less than 100. And yet we managed to get very good results, because here is, for example, is the annotation that we made with the center of the galaxy and the halo represented. And here is the prediction of the network, which predicts first that there is a halo and tidal features, and then that draws itself the position of the halo in these images. And the result is quite convincing, even though this image is very polluted by the bright halo just over there. So, and the network is also able to capture the cirrus, so the dust cloud that I showed you before. The network is also able to detect them on images. So to conclude, the detection and classification of tidal features is essential to constrain models of galactic evolution. To characterize them, we developed an annotation tool that enabled us to get the shapes of the tidal features. And from this, we can retrieve quantitative measurements. One thing that I did not talk about is that we can also apply this to simulated galaxies. So we are working now on mock images from simulations, and the goal is to perform exactly the same process, but for simulation, and then to compare the results from the characterization of observation and characterization of simulated galaxies, tidal features, to constrain the models of galactic evolution. And so deep learning can be trained on our annotation dataset to automatically detect tidal features. Thank you for your attention.
Thank you, Elisabeth. Questions for Elisabeth? Yes.
Thanks for the talk. So if 100 is the training and testing sample, okay, so if it's very small for machine learning techniques, why not using the simulation as a testing sample to then run it on?
This is also the goal, actually, because the goal is really to do the same process for a simulation. We are currently in this process, so we still haven't applied the machine learning to the simulation because it's still ongoing. But yes, the goal is to have another training set on simulated galaxies.
Other questions?
Thank you. You are doing that in the different bands. Do you see colors in the features, color trends?
For now, no. We're only working with the R-band images from CFS and MATLAS. And also, I didn't talk about the G-band in NGVS. So we also have access to the G-band MATLAS. So we have access to the color from MATLAS, but not for all the other to survey, at least not for CFS. So.
And we have a question online.
From Laura Parker, is the annotation tool available online? If so, can you provide the link in the Slack channel? Thanks.
Sure, the annotation tool is online, but actually we found out that in order to complete this annotation, we need a lot of talking between the people annotating and because we want to have a coherent set of annotations to be sure that people annotate in the same way and so that the results are comparable. And we tried this process with interns for now, with 3 interns. And yeah, we would need a lot of discussion before annotating, but I can send the link in the chat.
Okay, other questions? Okay, seeing none, let's thank Elisabeth one more time.